First, the homework for today, which was calculating vector potential and the magnetic field for a long wire by using a line integral. And then we'll begin a recap of Chapter 3, the Magnetostatics. And I have also I have some midterm grades to give you today, which you could probably figure out yourself. But anyway, I want to do that at the end of class. It's just homework and one test. We're about to have, of course, another test, but that's too late for me to include in this. That will be Monday, so we have practice tests Friday. I'll send that out by email right after class. And in fact, it's last year's test for Chapter 3. And of course, it's Chapters 1 through 3, but emphasis on Chapter 3. And then we'll have the test on Monday. Okay, now this problem of calculating the A field and the B field around a long current carrying wire is reminiscent of a problem that we had in Chapter 2 where we calculated the phi and E around a line charge, a long line charge. And so by long, what we mean specifically is this. In fact, what we're calculating is the A field and the B field at a point, a distance y above the midpoint of this line. And by long, we're going to make eventually make the approximation that the line is much longer than this distance y above the midpoint. By the same process, you could calculate A and B anywhere, but the integrals get a little bit more complicated, and by making the assumption that the point is above the midpoint, it just makes the integrals a little bit simpler. The evaluation a little bit simpler. So to get you started on this, I did that. So there's an analogy here to the line charge where we have a charge distributed over a line of length L, and again we wanted to evaluate phi and E above the a distance y above the midpoint of that long line. And the idea here is, as an example of the following, given the general question is, given, for example, the charge distribution, can we go directly to the electrostatic potential and the electric field? How do we do that? And likewise, if we have the current volume distribution, how do we go directly to the vector potential and the magnetic field? So generally speaking, this is done in the following way. Remember that if we have a little piece of charge, dq, which is a charge density times a volume element, so there's a little volume element here, and there's a little piece of charge, that the contribution to the electrostatic potential is just the magnitude of that charge divided by the distance to the location where we want to know the field. So R is here. We want to know what the field is. This is script R, which is the third leg of that triangle, and the magnitude of script R then is the magnitude of that difference, R minus R prime. Okay, and that gives us a little contribution to the electrostatic potential, and if we integrate this, and it's in principle 3 dimensions because we have a 3-dimensional charge distribution, that will give us phi at R. And this, written then in terms of the charge distribution, charge is a volume integral. And we don't go in this class into detail about how to do volume integrals, but if you're learning how to do volume integrals, then you can figure out how to do that. And very often we make the assumption that rho is uniform over some region, and so this is a volume, the integral is just over the volume. In the case of the line charge, we have, instead of rho dV, we have lambda dx prime, where x, now we put the coordinate system here centered on this line, and x is along the line, and y hat is perpendicular to the line, like that. And so a little piece of charge dq here is lambda dx prime, and so evaluating phi at a distance y above the midpoint there is just an integral lambda dx prime over the distance, which is going to be x prime squared plus y squared. this phi. And the same strategy will help for finding phi anywhere, not just above the midpoint, and around any charge distribution, not just the line distribution. So this is, in general, how one would proceed. We've used Gauss's law and other tricks to try to find the electric field and back out the electrostatic potential for special cases, but this would be the way, if you had some kind of rather complicated charge distribution, this would be the way to do it, to determine phi. Okay, and and then E, by the same token, would be to evaluate, here's the charge, and then what we need is we need R vector over R cubed, and so that becomes a little bit more complicated there, but you can set that up. So, and you could also, in this case, get E by taking the gradient of phi, negative gradient of phi, so you can do it either way. Okay, so that's what we did before, and I wanted to, and it's just an extension of the same principle, but analogous for the electrostatic potential. So the electrostatic potential at location R is an integral of J R prime dV prime over, again, the magnitude of R minus R prime. So this little piece of current contributes to the vector potential, again, according to its magnitude and direction, and weakened by the distance from the source to the location A. The thing is, here you have to remember that we have this is for magnetostatics here, and we have to, so there's the condition that it's instantaneous propagation, and also we have to remember that J here has no divergence, and in other words, J only curls in this. We can only allow that. So we have that restriction in magnetostatics that we've only considered that. Okay. In a later chapter, we'll see how to make it more general. But it's and it's from this prescription. Actually, you can sketch the A field around a kind of general current distribution. In the case of the wire, we have the current flowing like this, and so the J dV prime, again, if we're choosing the coordinate system x hat and y hat like this, that will go to I x hat dx prime. So in other words, it's a little section of the line. It carries total current I in the x hat direction. And so now in this case, A, that special case here, and this is a volume integral. So, but now it becomes a line integral. Oh, there's a 1 over c here for CGS. Excuse me. So I over c integral also in the x direction dx prime over square root of x prime squared plus y squared minus L over 2 to L over 2. Okay, so it's the same integral actually that we were doing for phi, but it's now notice I did a couple of things here. Be careful here. X hat is just a common factor, so I pulled it outside of the integral. There's no contribution to, y has no component in the y, or I'm sorry, A has no component in the y hat or z hat directions. A is pointing along the x direction because there's only current in the x direction. Now notice the other thing that we assumed here, I pulled I outside of the integral. I does not depend on x prime. That means that the current is uniform along the wire. What would happen if the current were not uniform along the wire?
I would be a function of x.
Yeah, I is a function of x, I prime. But why that would actually violate the magnetostatic condition. Can you see why that would be? What would happen if I is not uniform along the wire? Yes, ma'am, exactly. Charge builds up. There's a divergence of the current. The divergence, remember the divergence of J, excuse me, I need to use the same notation we've been using. The divergence of J, remember, would be the derivative with respect to x of Jx, and then there's no Jy or Jz here. And so this would in fact be the divergence of I, or proportional to the divergence of I, or the derivative of I with respect to x. So in other words, if I have a bunch of current flowing here, but then only a little bit of current flowing here, God bless, then I must have charge building up there, right? Because it stops flowing, and that means the charge is going to be building up. So the magnetostatic condition requires that the current in this wire has to be the same all along the length of it. Okay, so, all right, so there's the integral, and the form of the integral then, a y as a function of y. Doing this integral and evaluating it, and so you can see here in the solution that I gave you, looks like this. This is using the indefinite integral and evaluating at the two limits. Okay, so that's perfectly valid for every value of y, but remember we assumed it's right on the midpoint, so but it works for all values of y. We have not yet made the assumption that L is much greater than y. So this is valid for any length of line. But we want to connect it back to the argument we were doing before with Gauss's law, which gave us easily the A field and the B field near the middle of the long wire. So we want to make the assumption here that y is much less than L. And so for that, you want to remember how to do the Taylor series, and I'll make it show you how it's easy to do that here based on what you know already from Taylor series. Let's factor out an L, which is the big scale. L is the big scale. And now we have left in the square root a small piece, 1 plus something very small. Y is much less than L. So we have the square root of something small is approximately equal to 1 plus a half of the something small. 1 plus W is approximately equal to 1 plus a half W for W much less than 1. Okay, so then we can replace everywhere this is going to be approximately equal to L plus 2y squared over L. I'm going to take the factor out that L, distribute it across there. Okay, so that's approximately equal to that for y much less than L. And so if you carry that out and put that back into the expression that we have here for A, then you get that the leading behavior for the A field is in fact then just 2I over C natural log L over Y. And if I remember that the log of the ratio is the difference in the logs, I could rewrite this as 2I over C natural log L minus 2I over C natural log Y. Oh, all of this is in the x direction here, x hat. Okay, now you can understand that negative sign, right? We said that in our expression for A before, Mr. Bicot noticed that there was this funny negative sign of A has to be in the direction of the current. Why is there a negative sign there? Well, this is the reason why. Here's that big constant that I said was going to come out. And remember, L is bigger than Y. In fact, L is much bigger than Y. So this constant on the left is much bigger than the thing on the right-hand side. Okay, so now this is the expression for the A field near the middle of the wire, middle of a long wire. And this is what we could compare to our result before when we did Gauss's law and we extracted what, I'm sorry, not Gauss's law, Ampere's law in this case, and we extracted what A should look like. And I'll go over that, the argument here in a minute. Okay, so now the expression for the B field, I could just take the curl of this in this case, because A is only dependent on Y. I can take the curl of that and I can find the B field from that. The alternative is to actually do the integral, and the integral in that case, the general integral is the current density, current volume density crossed R vector divided by script R cubed dV prime, which in this case, for the line current, B is equal to, oh, there's a 1 over C here. I keep forgetting. So I over C integral of x cross R over R cubed dx prime from minus L over 2 to L over 2. And I have to remember here that script R is going to be negative x prime x hat plus y hat. Work that out. Okay, so you could do that integral, which actually turns out to be an easy integral to do. And you can see when you take the cross product here, x with r, x hat with r, the part of script r along the x hat direction vanishes when you take the cross product, right? We have negative x prime, x hat, cross x hat, but that gives 0. Plus then y times x hat cross y hat, and that's z hat. So this is equal to y times z hat. And then our integral is going to be b is going to be in the z direction and depend only on y. So it is I y over c z hat, and then we have okay, which is an easier integral to do. Okay, and so this gives, in the general case, 2i y, 2i over c, and then we have in the denominator here L squared plus u 4y squared after applying the limits. Oh, there's a y here. Here we go. Okay, and then making the argument that L is much greater than y, you can see this piece in the denominator here can be approximated simply by L to leading order. So for very long wire, near the middle of the wire, oh, I'm sorry, there's a factor of L up here as well, which cancels that L. There we go. Okay, now I got it right, because it was starting to look like I had a missing factor. There we go. That's the B field we get from that. Okay. Now let's go through the Ampere's derivation of this Ampere's law. We can, to compare this, which is, again, analogous to Gauss's law. We have a very long wire carrying current, I. We can draw a loop around that wire. Let's draw that loop, make it a circle that's concentric with the line. And so from the in view, the current is coming out. We're going to draw an imaginary circle around that. This is not a physical circle, it's just an imaginary circle that, and we're going to use that to apply Ampere's circuit law. The integral of B dot dl is 4 pi times the current that pierces that loop, which in this case is just the current that's in the wire. Okay, so now we have to go through the similar sort of argument here. We're going to, here's dl is a little piece, and we want the magnetic field, and we notice that the magnetic field is parallel to dl all the way around, so that B dot dl is just B dl. And we notice that B is the same all the way around. The magnitude of B is the same around the circle. So this just gives us the integral of B times this dl, which is just the circumference of the circle. So this circle has radius r. So this is 2 pi r. And that equals, okay, there should be a c here. I keep forgetting my factor of c in CGS. Okay, so solving for B, we get 2i over CR, which is the result that is analogous to Gauss's law, finding the electric field around a long wire, along a long line charge. So the B field circulates tangentially around the wire and diminishes like 1 over the distance. Just like the electric field points radially around a line charge, points radially outward, but diminishes like 1 over the distance. And that's exactly the result that we got here at the bottom here. It's 2i over c times the distance from the wire. So, questions? Very much analogous to the calculation that we did for the in chapter 2 for the line charge. Yes, I'll get Ms. Myers first.
Can you go back a slide?
Go back a slide, yes, ma'am.
To the bottom. How'd you end up with y hat at the end?
Oh, excuse me. I should not have. And you very patiently kind of thought about it. Now I'm going to ask. I mean, he never makes mistakes, so it couldn't be right, could it? Yeah. Thank you, ma'am. Mr. McKenna.
So for example, the magnetostatics, that
Yes,
would
sir.
not hold under like a copper wire, correct? Because that has resistance in it inherently.
Well, as long it doesn't have to be a perfect conductor. It just has to be a current has to be flowing uniformly. In this case, along the wire. There can't be any spots where it starts charging up, so it has to flow uniformly along the wire. And it can't change in time, and we can't move the wire.
Okay.
Those would be the conditions for magnetostatics here. The wire has to stay in place, and the current can't have any place where it stops and charge is building up. And the current has to be constant in time, no change in time, for the strict magnetostatic condition.
Okay.
So even if it's a real piece of copper, it still can follow the strict magnetostatic condition. You just don't let the current change, you don't move the wire, and you don't have any spots where there's charge building up, like a capacitor, like a gap in the wire or something like that. Okay. Mr. Friedel.
So Stokes' theorem relates Ampere's law to the curl.
Exactly, that's correct. Just like we had in Gauss's law. So let's go to this case. Here's part of the analogy between Chapter 2 and Chapter 3, that is between the electrostatics and the magnetostatics. So we had Gauss's theorem, which was that if we look at the flux of an electric field coming out over a surface that completely surrounds a volume, so this is a perfectly enclosing surface, there's an inside volume and an outside volume. It's completely divided. And dA points outward from that. Then Gauss's theorem says that this will be equal to integrating the divergence of E over a volume. And this is true for any vector field, not just the electric field. But now we're going to apply Maxwell's first equation. It says that the divergence of the electric field is proportional to the charge enclosed. So if we substitute, so this is Gauss's theorem, which is a mathematical theorem holding for any vector field E, but now we're going to make it an electric field, which is diverging around a charge density. We put that in there, and we find then that the flux of the electric field is now at 4 pi times the integral of rho dV. Well, the integral of rho dV is just the charge. So this is 4 pi times the charge enclosed. And now this is Gauss's law. Gauss's law is expressed in two forms, either the integral form or the differential form. So here's the differential form, and here's the integral form. These are, this is usually what you see as Maxwell's first equation. Both of these could be called Gauss's law of electrostatics, which is specific to an electric field. So Gauss's theorem is a mathematical theorem. Gauss's law is having to do with the nature of electric fields, the charge density. Now let's look at the same thing. There's an analogy here to magnetostatics involving Stokes' theorem. So let's start with Stokes' theorem. The circulation of a vector field is going to be equal to the area integral of its curl. Add up all the curls over the area. This is Stokes' theorem. And again, Stokes' theorem is a mathematical theorem for any field. But I'm going to now say, let's use this on the magnetic field by recalling Maxwell's equation for magnetostatics, which is that the curling of B is caused by a current density. And if I substitute that into Stokes' theorem now, I can see that the circulation of the magnetic field around an imaginary loop, and now I'm going to integrate J dot dA, but that's the current, the total current that pierces that surface. So this is 4 pi over C times I enclosed. By that I mean the current that pierces the surface, the little disk. And this is Ampere's law, Ampere's circuit law. So I'm combining mathematical theorems along with, again, a differential form, differential and integral form of Ampere's law. And of course, what you recognize that is Maxwell's, the differential form is Maxwell's fourth equation, which has really two forms. Usually you see it in the differential form, but it's equivalent to write it in the integral form. So there's a parallel. In the first case, we would have a Gaussian surface, which was some kind of closed surface that would surround a charge, like a cylinder or a sphere. In the second case, we have a closed loop. And it's easier if that loop is planar. Okay, it doesn't actually have to be, but it's going to be a lot easier to make it planar to understand what we're doing. And so in this case, we take a loop surrounding a wire carrying current, and then we can figure the magnetic field from that. Does that help, Mr. Friedel? Is that it? That's a good point. There's a lot of correspondence between, a lot of contrast and comparisons between electrostatics and magnetostatics. Okay, so now let's continue this. We have two equations in electrostatics. The divergence and the curl of the electric field. This physically represents the idea that the charge density, a charged body, generates in the plana around it, the parts of the plana around it, an electric field. And that electric field diverges from this charge in this fashion and does not curl. So there's no circulating part of the electric field in electrostatics. So what are the conditions for electrostatics? We have stationary bodies, stationary charged bodies. The charge doesn't change. The charge is constant, the bodies stay put, and you can express that by saying one thing is that the derivative of the current density is 0. Excuse me. I did not mean to say that. The current is 0. There's no current. Everybody stay put. That would be the only way. You can have charges, but there can't be any current. It can't be moving around. Okay, for magnetostatics, you have stationary currents, meaning that the wires can't move and that the J must circulate. In other words, that the J is constant, so there's no time derivative to J, and the divergence of J is 0 everywhere. That's the magnetostatic condition. And the two corresponding equations now are that the divergence of B is always 0. B never diverges. But that we can cause a curling B by having current density in the vicinity. Well, in that vicinity, the B will curl around a current density like that. Okay, so you see that there are two equations here, two equations that are zeros, and then two equations that connect the electric field or the magnetic field to the source. So here's the source of the electric field and the source of the magnetic field. So what causes an electric field in the plana? A charged body. What causes a magnetic field in the plana? A charged body with impetus. That's what makes current, what we call current. So the measure the current volume density is a measure of the rate of change, rate of displacement of a charged body because of its impedance. And we also had the condition that, excuse me, doggone it, did it again. The divergence of J in general relates to this, but because in electrostatics and magnetostatics we don't have charge building up, so that means either the current is zero or the current has no divergence. Effect is even a constant without divergence. Okay, but this is the more general expression that a divergence in the current density results in a charge up, a charge building up someplace. Okay, now that's in terms of E and B. So remember, going back to the Helmholtz theorem, we said if we know the curl of the field and its divergence everywhere, we can reconstruct the field. And so this says in principle, we know the curl and divergence of E, so we can reconstruct that electric field. And we know the curl and divergence of B, and so we can reconstruct that field. Well, that's exactly what we did up here, right? At the beginning, we wrote down the solution to this, E in terms of rho, and B in terms of J. I wrote that down. It's an integral, and we did that example. Okay, now that doesn't mention the vector potential because the curl of E is 0. That says that there's no curling part of E, and so E can be written purely in terms of a gradient. And so there's a phi field. Physically, phi is the further specification of the electric field. It gives us more information about the electric field that's present in the planet. Likewise, because the magnetic field doesn't diverge, it means we can write B in terms of a curl of a vector potential. The fact that we have these two equations mean that we can do with one or the other. In other words, that the curl of E means we have a phi, and the divergence of the curl of E being 0 means that we have a phi. And the divergence of B being 0 means that there is a vector potential. The proof of that is you're going to have to wait for. It's the best intuitive discussion that I can give you is a field that doesn't circulate is going to be one that is like a gradient. And a field that doesn't diverge is going to be a circulating field, which is the curl gives you something that circulates. Okay, so you can plug these into the source equations. So the divergence of E is 4 pi rho. If I use now, express it in terms of phi, this becomes the Laplacian of phi, which is the Laplacian is the divergence of the gradient. It's minus 4 pi rho. The Laplacian is the divergence of the gradient. In Cartesian coordinates, it looks like the sum of second derivatives, like this. That's the Cartesian form of this is called the Laplacian. And this equation is called Poisson's equation. And you saw at the beginning we inverted Poisson's equation to find phi in terms of rho. Here if we have phi, we can find rho. By doing an integral, we can invert Poisson's equation to find phi directly from rho. Okay, and in the same way, we have the curl of B is 4 pi over Cj. Let me get rid of that little mess there. Okay, and now I'm going to say, well, let's use the fact that B is the curl of A. Substitute that in. And that takes a little bit of manipulating, a little bit of working here, because we have the curl of the curl. So the curl of A, and that takes a little work to show that that actually simplifies to Laplacian of A is a negative 4 pi over Cj, like that, which is a funny looking equation. If you're not used to working with Laplacians, that's kind of a funny looking equation. It's actually 3 different equations. You could write it for each component of A like that. Each component. So it says that the current in the x direction generates a field in the x direction, and the current in the y direction generates a field in the y direction, and the current in the z direction generates a field in the z direction. Okay, and we can invert this to an integral like we set up at the beginning of the lecture up here. So I'm going to go up here. Okay, so here's the inversion of Poisson's equation. So that's the inversion of Poisson's equation. Gets phi directly in terms of rho, and here's the inversion of the corresponding equation for a. The Laplacian of a is 4 pi over cj, negative 4 pi over cj. So you can invert. Okay. All right, so all these things are interconnected, and you need to kind of understand the terrain, the map. We have differential forms, integral forms. They're interconnected with each other. You can use an integral form to solve a differential form. So there's a kind of a snow of symbols coming at you, and you have to blizzard even, and you have to kind of sort this out, or otherwise it's all going to look just all the same, right? It's going to be like trying to find this polar bear in a snowstorm. You need to sort this out in your mind so it's not like it's all looks the same. And so, questions, Mr. Friedel.
So does the Laplacian specify a certain function, like dot product or cross product? Because the Laplacian of A means crossing it twice, but then the Laplacian of phi means dotting it twice.
No, not actually. So to do this, if I substitute for B here the curl of A, I have to demonstrate that it's not always true, but it's true under the conditions that hold here. That this is the negative Laplacian of A, and that holds only for this magnetostatics condition. So it's only true in this particular case. And the Laplacian is this, given up here. Okay. So why that should always be true takes some. Why that should be true in this case takes a little work to demonstrate.
So in the Laplacian, like when you're doing del to the second A, there is no dot or cross product involved.
Correct.
Okay.
Correct. Yeah, and that's why I wrote it like this, because it looks a little funny there, right? And so it's actually like 3 equations. It looks kind of funny. A Laplacian acting on a vector looks a little funny, maybe the first time you see it. And what does that mean? And that's what I mean there. Each Cartesian component satisfies an equation. That's like Poisson's equation. It's a little funny. Okay, so the remaining thing to have in mind is what I call the catalog of geometries, electrostatics and magnetostatics. And so again, it's helpful to draw comparisons. We talked about a point charge for electrostatics, but there's no corresponding thing in the magnetostatics catalog. So to make correspondence, we drop that one. Let's go to a line charge, and in this case, a current-carrying wire. And again, what we're looking at is the fields close to the middle, far from the ends, close to the middle, right? And we can use Gauss's law in the left-hand case for the electrostatics and Ampere's law in the right-hand case to get a simple argument. Or we could actually evaluate the integrals and take the Taylor series like we've done. Okay, so phi and E. E drops off like 1 over r, 1 over the distance. So it's going to be 2 lambda over the distance. The magnitude of E goes like 2 lambda over distance, and phi goes like negative 2 lambda log distance. And again, there's a funny negative sign. Let's see. No, is it negative? Hang on. No, yes, it's negative. It's negative. Yes. Whereas A, we have the magnitude of A and the magnitude of B. A is parallel to the line, and it will go like negative 2I C natural log of the distance, and B goes like 2I over CD. Right? You see the parallel between those? Right? Yes? No? Can you see the parallel there? The field strengths? Okay. They're not exactly the same. It's interesting to compare them, but they're different in important ways, right? A is pointed along the line. We have a vector potential, not a scalar potential, and so forth. But you can now, with this knowledge, you can do something like, suppose that instead of a line, we have a cylinder, and we put charge on the cylinder. And over here, suppose that we have, instead of a tiny wire, we have a wire with current flowing on the skin of the wire. And we can go through the same argument. So inside, we find that there's no electric field in the left case. There's no electric field inside. There's electric field outside that looks exactly the same as the wire, as the thin line. So in this right-hand case, you could go through Ampere's law. You would draw either a circle that goes around the outside or a circle that goes around the inside. If you draw the circle around the inside, there's no current enclosed. If the current is flowing on the skin of the cylinder. So that would say the magnetic field inside is 0, which is correct. There's no magnetic field on the inside of this. And the current is flowing on the outside of the cylinder. So there's no magnetic field. B is 0 inside, just like E is 0 inside. So you could construct a coaxial situation, a coaxial cable. You could have 2 cylinders with opposite charge, for example. You would have an electric field inside, and you'd have an electric field between the cylinders, but inside the innermost and outside, you would have no electric field. So you'd have say a plus sigma and a minus sigma. You have a charge density. No, that's not correct. Same, plus lambda and minus lambda. Okay. Then you have canceling electric fields, and you have no electric field outside, no electric field inside. You have only electric field between. In the same way, if you have a coaxial cable that's carrying current in one direction on the inside, on the skin of the inside cylinder, and current flowing in the opposite direction on the skin of the outside cylinder, then you would have magnetic field only in between. But magnetic field inside and outside of the whole thing, you have 0 magnetic field. You have a coaxial cable, and that's why coaxial cables are used in labs to try to avoid stray magnetic fields generated by currents in the wire. Okay, so the point is that you can take this simple first case and kind of generalize it and work your way up to more complicated geometries, but still basically has the same basic cylindrical symmetry. Mr. Bacot.
On the top drawings,
Yeah.
just like the single cylinder,
Yeah.
there's no E or B field inside, but there is a phi and an A.
Yeah, that's right. But okay, so if E is 0 inside, what does phi do inside? It's constant. So let's take that top case. Let's plot phi as a function of distance from the center. So it goes that logarithmic form outside. So phi must be a constant like this. Let's see. I've got it wrong here. Phi. Have it upside down. There we go. Phi does that. Here's the radius of that. So it's a single cylinder. Phi is constant inside, therefore no gradient, therefore no electric field, and then it falls off logarithmically outside. Okay, now let's do that same comparison. A single cylinder carrying current on the outside of the cylinder. Let's look at the A field. The A field will have A parallel to the wire, and no other components. But what does A look like inside? It must be constant. It has no curl. Right? It can't depend on. If it had any dependence on X and Y, it would have a curl. So A will drop off like that. Drops off logarithmically outside. Inside, it must be uniform. Have no magnetic field inside. Let's see. That must be true. Yeah. Pretty sure that's true. I've got to think about this for a minute. Hang must be true. Yeah. Okay. You can have, remember, you can have non-uniform fields that don't have a curl, right? You remember that? That we found A fields that vary but don't have a curl. So we have to be a little careful. That's what I'm worrying about here, and what I just said I think is correct. Okay. Okay, so now let's look at a planar geometry. That's another situation. Oh no, let's. There's another situation that we have with magnetostatics that we don't have with electrostatics. Let's go back to that cylinder. We could have current flowing along the skin outside like this, flowing parallel to the line, to the cylinder. Okay. The other thing we could have, we don't have this variation in electrostatics, we could have current flowing on the skin outside like that. Excuse me a second. Okay. So, what kind of field would that generate? You recognize it?
Solenoid.
It's a solenoid. This is a solenoid. And remember, we said the solenoid has a B field only inside, not outside. And the current in this, in the top case, there's no B field inside, only outside. So you might want to go through the exercise of sketching the magnetic field and the A field in both of these cases. You don't have something like this in electrostatics because in magnetostatics we have the current direction as well as the intensity, so we can change the current direction. And so there's a richer, the magnetic field is richer for that reason. Okay, and then we could do planar geometries. I should go back here. Notice, remember, in the solenoid, the magnetic field inside is uniform. It's the same everywhere inside. So that's one way of generating a uniform magnetic field. Okay, then we had planar geometry, the electrostatics. We take a charge distributed over a plate. And again, with the magnetostatics, we have current that's smeared out over the plate. And we said that phi and E, remember how they go? E is a constant. And phi is linear. And so that ought to suggest that A is also linear and pointing in the direction of the current. And that B is a constant. Again, that's near the center of these things. Now, you got to stay away from the edges, near the middle. So this is close to the middle of a large plate. That's where these simple behaviors hold. And you could use Gauss's law to demonstrate that in the first case and Ampere's law to demonstrate that in the second case. And then now you can combine sheets. You could, for example, put oppositely charged parallel plates like this, make a parallel plate capacitor. Now we'll have a uniform electric field in between, and phi is linear now between, and no electric field outside. And likewise, you could take two parallel plates, have current flowing, two parallel sheets like this, and have current flowing uniformly distributed over the sheets in opposite directions. And how will the magnetic field look? In between and outside. So in here, the E field is uniform, and outside E is equal to 0. Well, you get the same thing for the B field. B is 0 outside, and inside B is uniform, but it's not in the direction that the electric field is, right? Let's see, so it goes this way. The B field points that way in between the plates. No, I got it backwards. Let's see, did I get it backwards? Hang on. Hang on. Somehow I think I'm backwards here. Yeah, I got it backwards. It goes kind of into the plate, into the page here. So you could make a uniform B field that way. So you could make it a uniform B field in a solenoid, or you could make a uniform B field by having sheets The challenge is to make sure that the current distribution is uniform in all those cases, right? That you have to have uniform distribution of the current in the top plates, or in the solenoid you have to have a uniform distribution going in that fashion. And of course, the way we make an almost solenoidal field is to take a wire and wind it like this. And that's not exactly the perfect solenoid there because of the gaps between the wires, but that's pretty close. And if you make the wires, pack them in, make them thin and pack them in, well, you get a very close to uniform, almost perfect, ideal solenoid field. In practice, this other thing is a little harder to do. You have to distribute the current uniformly over the sheet. That's a little harder to do. Whereas the solenoid is a pretty easy way to make it almost uniform magnetic field. Yes, sir, Mr. Bacot.
Is that coil of wire not like how you make an electromagnet?
Yeah, that's a solenoid. Yeah.
Well, how's it a magnet then if the magnetic field is on the inside?
Ah, okay. So, good question. He wants to know how does it make this a magnet? Well, of course, an electromagnet, there's another component, right? What's the other piece?
Like the piece of metal.
Yeah, you put a piece of iron core in there, generally, or a metal that has a high magnetic susceptibility, so it will respond. So it enhances the magnetic field. Even without the iron core, there's a magnetic field generated by this, and what you're seeing is the fringing field. Okay, so there's fringing field that comes way out, all around here, but up close, up in this vicinity, just outside the solenoid, and you're away from the ends, there's no magnetic field there. It's very weak. And any magnetic field that's present is because this solenoid has either because of the finite winding, the wires have finite thickness, and